Hello everyone, welcome to the next lecture of electronic devices. We are talking about diodes. So in the last lecture we started with more applications of the diodes, and we started with looking at the kind of a block diagram for a DC power supply. We talked about a little bit about the transformer, a step down transformer that we need as a first kind of a component in the power supply. And the second component we need is a voltage rectification or a rectifier circuit. We talked about half wave rectifiers and full wave rectifiers. In full wave rectifiers we talked about a center tap rectifier circuit, full wave rectifier circuit, where we used a center tap transformer to rectify the full wave of the input waveform. Today we are going to discuss another full wave rectifier called as a bridge rectifier, right? So what we have done by now is, so we started with this big waveform coming from AC mains, 120 volts. We ended up converting it to something around 6-10 volts that we need using a step down transformer, and that depends on whatever our charging requirements are. So with that, after that, we wanted to convert this thing to a full wave rectification. We talked about half and full wave rectifiers. In this lecture, we're going to talk about one more full wave rectifiers, and then we are going to more importantly talk about the next step, in which what I want is I want to create this into a much more closer DC waveform, something like this, and we can do that by by developing peak detector circuits and using some capacitor based filters. So we're going to discuss that, how we can do this thing in today's lecture. So this thing is what we're going to mostly talk about today. And after that, we kind of, you have seen this waveform, right, where the mean value is somewhere over here with a 10% variation. We can feed this to Zener shunt regulator and we get a constant DC. So that component we have already discussed in the previous lectures. Okay, so let's start our lecture today. So in this lecture, we're going to discuss the other type of full wave rectifier known as bridge rectifier. Okay, it is called as a bridge wave rectifier or a bridge rectifier because the configuration of that looks very similar to a Wheatstone bridge. I don't know if you have studied that Wheatstone bridge in your previous, probably you have already, in your other courses, other fundamental electronic courses. But the configuration looks very similar, so we can we use that. That's why you kind of use the term as a bridge rectifier. Another important thing in terms of other type of our transformer, other type of the rectifier circuit that we discussed earlier, center tap. This will not require a center tap transformer, so it's kind of a simpler in that way. However, now this will require 4 diodes compared to 2 diodes that we used in center tap transformer. So since this will require 4 diodes, however, note that diodes are usually very inexpensive. And another advantage is we have some ICs available which has all of these 4 diodes in a bridge rectifier configuration already available. So that in that sense, it is pretty simple to use a bridge rectifier circuit. Okay, so let me draw the bridge rectifier circuit so we can start discussing how does it actually rectifies it, right? Okay, so this is our transformer, right? Okay, all right, so here's one diode, and then here is second diode, here is third diode, and here is fourth diode, a resistor R plus minus V naught, and then this is grounded, this is plus minus Vs. right? And here is our input, AC mains. Okay, now what we have over here is a transformer circuit. Let's also call this diodes as D1, D3, D2, and D4. Okay, now looking at the circuit, we can see that first is the transformer that is going to step down, and then we have a full wave rectifier in the configuration of a Wheatstone bridge. So that is why it is called as a bridge rectifier. We have 4 diodes compared to the 2 in the center tap rectifier that we discussed earlier. So let's see how does it actually does the rectification. So I'm going to discuss the positive cycle and the negative cycle. So let's see what happens in the positive cycle. So positive cycle. So what will happen in the positive cycle is, let me first draw and then I'm going to write it down too. So in the positive cycle, so for example, this is a positive cycle of a waveform. Your input is something like this, right? So let's first discuss the positive cycle. What is going to happen at the positive cycle is you're going to get a positive cycle here. So this means that this Vs will be positive, right? So you're going to have a positive here. So this means that diode 4 will be cut off. Diode 1 will be turned on. Okay. And now as diode 1 will be turned on, so what will be the conduction path? You're gonna have the current flow over here, then through the diode over here. At this point we can see that this potential is negative, so this is gonna turn off D3 as well. So we're gonna move over here all the way through the resistor, and then it is gonna go through the diode D2 and then back. So this is the conduction path of the current, where our D2 and D1 is on, and D2, D3, and D4 is off. So in a positive cycle, Vs is positive, right, at secondary winding. So what this will do is this will make D1 and D2 on, and D3, D4 off. And conduction path will be through D1, then through R resistance, then through D2. Okay, right? So this will be the current conduction path. Look at the look at the conduction path. It's very important in terms of defining where our rectified output is going to appear. Now let's look at the negative cycle, and I'm gonna write down the negative cycle. So let's look at the negative cycle of the waveform, right? So now we have now let's suppose that at our input we have a negative cycle. So if we're gonna have a negative cycle now appear over here at the output, so this means that my negative Vs, right? So this side will become positive, right? So minus Vs will become positive, right? So if this side will become positive, right? So this means that now my D3 will be on, and my D2 will be off, and my D1 will be off, and D4 will be on. So the conduction path now will be, so it will go all the way here, then it will go through the diode D3, then D1 is off, so it will move through R, and after moving through the resistor R, it will go through diode 4 and then back to the transformer. Okay, so let's write this down. So now we have D3 on, and we're gonna have D4 on, and we have D1 and D2. D1 and D2 are off, and conduction path is through starting with D3. So it will be D3, then through the resistor, then through D4, then back to transformer. So this will be the conduction path. Important thing to note down over here is two important things that I want to make points over here. So one important point over here is that look at the direction of the current in both the positive and the negative cases. It is the same. The current will flow through the resistor R in the same direction, right? So we have this thing and then we have this thing for the positive and negative cycle, right? So during both cycles, current will flow in same direction through R, right? So V naught, potential across the resistance, will always be positive, right? And that is why your this cycle will become this. Second point, I can write it probably in the next slide. But note that for every cycle, the diodes are appearing twice. So two diodes are appearing in a positive cycle. For example, in this positive cycle, we had D1 and D2 on. In this negative cycle, we have D3 and D4 on. So in the conduction path, we are coming across two diodes. So there will be a 2 times potential difference. So the output voltage now will be lower by 2 times the VD, right? So considering, again, this was considering the ideal diode, otherwise we're gonna have a potential drop of 2 times the VD in the peak voltage, and it is only gonna conduct once, assuming constant voltage drop model, it is only gonna conduct when it will become 0.7 volts. So let me write this down, and then I will also make a waveform. Since there are 2 diodes in series in conduction path, V naught will be lower than Vs by 2 diode drops, right? So this is what we said. V naught will be equals to Vs, or Vs, the peak value of the Vs, minus 2 Vd. All right. Let me quickly make the waveform as well for this. Okay, so let's suppose this is time and this is the voltage V, and let me first make input voltage. So let's assume that this is the input voltage that is going on. So let's make the output voltage, right? So we have already seen that the output will remain 0 until there is going to be a voltage drop of this VD here, right? And I can assume it to be somewhere like this, and then it's going to start to go all the way high and then come here. Now the negative cycle will also be rectified, since it's a full wave rectifier, and we're gonna get something like this, right? And this thing is also gonna go on. So the important thing to notice over here is that difference. So that difference, right? So this thing is V naught and this thing is Vs. So the difference over here is Vs minus 2 times the diode voltage drop. We can draw another waveform over here. So for example, if I will consider it as a positive Vs, I can also draw it as a negative Vs, just to make your life easier, probably. All right, for example, you can assume this to be a negative Vs. So this waveform is appearing at the negative of the secondary winding, and that is why when this Vs waveform will become negative, the negative Vs will become positive. Okay. So this is how the output voltage waveform looks like. It's a full wave rectification, one important thing to remember. And the second thing, output voltage has a 2 times voltage drop in the peak value. Now compare that, if I will compare this thing with the center tap again, with us in the center tap, we had 2 diodes. Over here we need 4, but 4 is pretty easy to come by. Another difference is in the form of using a center tap transformer is more expensive as compared to using a regular step down transformer. So that's an advantage of this. The third difference is in the center tap full wave rectifier circuit, we had only one diode coming across. So our output was Vs minus Vd. Over here it is Vs minus 2 Vd. Okay, great. So there's one more thing that we need to do for this transformer before we move to the next topic, and that is we need to determine the PIV value. PIV determination. All right. So let's determine the PIV of the bridge rectifier circuit. So I'm gonna go back here. It seems a lot cluttered. So I'm gonna make the rectifier very quickly here. Positive. Okay. And then all right. So just assume that there's a transformer over here. Or I can just make it quickly. Oh, sorry, it should be the other way. All right. Okay, great. Right. So this is our bridge rectifier, and in terms of I wanna make sure that the numbers of the diodes are the same: D1, D2, D3, D4. D1, D2, D3, D4. Okay, sounds good. All right. So let's determine the PIV. Again, PIV is a peak inverse voltage that is going to appear across the diode, and that will help us selecting the right diode to use in the rectifier circuit. Okay, so in that, so let's do step by step. Consider positive cycle. So what was happening in the positive cycle? So okay, I'm going to do this. So what was happening in the positive cycle? In the positive cycle, we had this thing on, this thing off, and then this thing off, and this thing on, right? So in the positive cycle, current flows through D1 and D3 becomes reverse biased, right? Okay, so current is going to flow over here and then through here, and this will become reverse bias. And if you remember, what is the voltage drop here? V0. So over here, at this point of that diode, we have a V0 that is appearing. So D3 will become reverse biased, right? And we are interested in finding what is the peak value of the reverse voltage that can appear across this D3, right? Okay. So V0, at this point during the positive cycle, the potential is V0, and at this point, what is the potential? We had, what do we have over here? We have plus minus Vs. So the potential drop over here is minus Vs, right? So the reverse potential reverse voltage and D3 equals V0 plus Vs. So that is the total voltage that is appearing across here. Okay, and now okay, so this is it, V0 plus Vs, and now let's see what is the maximum value of Vs that can appear over here. So the maximum value of the Vs, V0, so sorry, the maximum value of the V0, max V0 that can appear as Vs minus 2VD, right? Now going back, yes, Vs minus 2VD. So if I will put this value over here, right? So if I will put this value over here, Vs minus 2VD, then what I will get is, so this is the maximum, this is the reverse PIV determination, PIV voltage. So now my PIV will become V naught Vs minus 2VD plus Vs. So this will become 2Vs minus 2VD. And now as I can see that over here, the total potential drop, so we have, sorry, so this is V naught and Vs. The total peak inverse voltage across the diode over here is 2 Vs minus 2VD. Okay, sorry, just give me 1 second. I think there's a mistake in the in calculation I have over here. Okay. So I think the mistake is over here. Sorry. So ignore this thing. Sorry about that. And all right. So what do we have here? Peak inverse voltage. Let's do it again very quickly. Peak inverse voltage, we are interested in finding what is the maximum inverse voltage that can appear across any diode. So you can pick any cycle, positive cycle, negative cycle. Let's still pick the positive cycle. In the positive cycle, we determine that our D1 is on and our D2 is on, right? So our D1 is on, our D2 is on, and our D4 is off, and our D3 is off. Okay. Is reverse biased, right? So we say that, okay, our current is going to flow through D1 and then it's going to flow through D2 and then it is going to go back to the transformer and D3 will be reverse biased. So we are interested in finding the potential drop, the maximum potential inverse voltage that can appear across D3, right? So at this point, we are still going to have a V naught, but at this point, right, what do we have is the potential. At this point of the diode, what we have is over here is VD, right? So since this was forward biased, in this conduction path, our D2 diode was forward biased. So the potential drop across this diode is VD, right? So considering we have a potential drop across this diode to be VD, so that this is how we can determine it. So we're going to get VD over here. So now the peak inverse voltage is going to be equals to V naught plus VD, right? And then again, maximum V naught will happen when so this is what we determine the maximum V naught. So the maximum V naught is Vs minus 2VD. And this is, we are going to put over here. So our PIV will become Vs minus 2VD minus VD, so we plus VD, so we are going to left with Vs minus VD PIV. All right, notice that this PIV is almost half of the center tap one, right? So this PIV, so PIV is half of full wave rectifier. This, or bridge rectifier PIV, is half of the full wave rectifier, full wave center tap rectifier, right? So this is another advantage. Okay, great. All right, so this is another example of a full wave rectifier circuit, and this is how we can determine the peak inverse voltage of this circuit. All right, and yeah, sorry about that. Again, let me clarify this thing again, right? During the positive cycle, our D1 and D2 will turn on, right? That is why the potential drop across over here will be VD, the diode or the barrier potential drop, right, which is approximately equals to 0.7, or we can easily call it as VD, right? So this potential over here is VD, and the potential that is appearing over here is V naught. So that if maximum reverse bias voltage will be, if we will consider this loop, right? So if we will consider this loop, the maximum reverse voltage is going to be V naught plus VD. The maximum, yeah, and we can find out what is the maximum value of the V naught that can appear, which is this. Okay, so this is how you can find out the peak inverse voltage value of a rectifier circuit. All right, so we want to do one more thing after that in today's lecture, and that is how we can further reduce this variation. So right, so we ended up converting this to this, and our goal is to convert this something like very small ripple voltage, right? So this is, we want to convert it into a better DC, right? For that we need to develop another circuit that is called as a peak rectifier, right? So right now we ended up doing a full wave rectifier, a half wave rectifier, and this next thing is called a peak rectifier. So essentially this new term, peak rectifier, what it is doing, it is rectifying the variations in the peak voltage, right? So now this is going, and how we can achieve that? We can achieve that using a simple capacitor. Okay. All right, so let's do that. Let's do that circuit now, and the circuit is pretty simple. So we have over here, this is our input voltage, this is our diode, and here's our capacitor, and this is our V naught. So let's assume that this is your rectifier circuit. So whenever there's a diode, right, it's going to rectify the VI. And now we have connected a capacitor. And what this will do is, we are going to realize that this is going to provide us a much better DC waveform. And how we will do that? Let's analyze it. For easier, assume ideal diode. Now, so interesting thing is that now you can see that as all right, so let's assume some details here. So let's assume that VI is this, and the peak, this is VI, and the peak value of the VI is VP, just to make things easier. Now as VI goes positive, as VI goes positive, diode conducts and charge capacitor to V naught equals Vi, right? So what will happen is, during this positive cycle, as soon as this will become positive, we saw that in an ideal diode, as soon as the voltage will become 0 greater than 0, it will become a short circuit, right? So in this positive cycle, as soon as this positive cycle is going to start, the diode will be short circuit, and then a current is going to start to flow, and the capacitor is going to start to charge, and the process will continue till it reaches a peak value, right? And this is going to fully charge the capacitor, and the potential drop, the V naught, will become equals to VP, or the maximum voltage that is appearing over here. So right, so if I will draw the output, just let me, okay, so it is going to charge all the way here, right? Okay. And this is output voltage V naught. All right, VI, and our maximum voltage that is appearing over here is VP. So this is going to charge the capacitor until it reaches VP. Okay. Now what will happen during the negative cycle, or as soon as the voltage will start to drop? Now as voltage VI will start to drop, diode will be reverse biased, and not even in the negative cycle, right, in this entire thing. As soon as this voltage will start to drop, this means that my output over here is VP, which is more, and my VI is less than VP. right? So the potential drop across over here, right? So this was V naught and this was VI, and I can see that when this is VP, when my output voltage is VP, but my input voltage is less than VP, the diode will become reverse bias. Right, so as soon as it starts to fall below the peak value, the diode will become a reverse bias and off or open circuit. And a capacitor remains charged, right? So capacitor remains charged. So the output is, so in this kind of an ideal case, so capacitor will remain charged, and it is going to remain charged forever, kind of. Capacitor will keep its charge kind of indefinite because there is no way to discharge, because there is no way to discharge. Right, over here we can see that there is nothing connected after the capacitor. So in this ideal circuit, there is nothing. Once the capacitor will be charged, there is no way that it can discharge. So we're gonna get a constant voltage across the capacitor, right? So our output voltage over here is kind of an constant. So this circuit provides a DC voltage output equal to peak input voltage. All right. So this is again one of the very basic things. This is, by the way, this is also known as a peak detector or a peak rectifier. Peak detector or a peak rectifier. It is called as the peak detector because it is going to detect the peak and then remain constant, right? So again, in our case, we were, after getting a full wave rectification of the waveform, we were interested in to supply a constant voltage, right? So we saw that if you're just going to connect a capacitor after the diode, after the rectifier circuit, we can see that as soon as this voltage waveform is going to start more than 0 or equal to 0 and then move higher, the capacitor is going to start to charge because the diode becomes short circuit. Or there's going to be, in case of a real life situation, there's going to be a 0.7 or a VD voltage drop. So anyways, once it will be charged and at the peak input voltage value, and once the input voltage will start to fall down from the peak, the potential drop over here, VI, will be less than V naught, and that is why it will become reverse biased. And then during the entire cycle, it will remain reverse biased. And the same thing will remain true, that it is going to supply the constant voltage indefinite because there is nothing else to discharge. However, this is not true in the real world applications because we are going to have a load, right? We have, after that, we have something else to charge and connect, so there is a load. So now we are going to discuss some more like a real life situation in which we are going to have a load as well connected to the circuit, right? Okay. Okay. Practical case, and we are still assuming ideal diode just to make our life a little easier. All right, now I'm going to make a circuit. So our circuit is kind of pretty much will remain the same with some variations in it. All right, so we have this, and then we have this. So now what we essentially did is, after the capacitor, we're going to have some form of a load, and we will see now how will that impact our values. So this is output voltage I'm interested in. This is the input voltage. Again, this diode D here. The current over here is, let's call it as ID. The current to the capacitor, let's call it as IC. The current to the resistor, let's call it as IR. Or yeah, we can, let's, since I'm considering R, yeah, so in terms of keeping the nomenclature the same, I'm going to call it as a IL. This is the load current that is flowing through it, right? So this is IL. All right. So let's see how this will work, how this real scenario will work, and it will be a slightly more complicated now. We will realize it shortly. Okay, so I'm gonna draw this. So now assume that we have a waveform, and I am more interested in making more waveforms here for a variety of reasons. So this is our input voltage, and again, input voltage is a peak value. And let me make an output here as well. Okay, so let's call this V naught. It kind of helps with this dotted lines. Okay, sounds good. I'm going to draw the output voltage in a second. All right, so what we have now is we have a load resistor is connected in parallel to capacitor. Right, our basic understanding is going to remain the same, or our basic reasoning is gonna remain the same. What will happen is right at the start of the waveform, right at the start of the waveform, we are assuming an ideal diode. It will become short circuit, and we're gonna start to charge the capacitor. So the capacitor will be charged all the way up to the peak at this value, right? So it is going to be charged at VP, right? For sinusoidal input, the capacitor will charge to VP, peak value of that, right? And after that, right, we saw that what will happen as soon as it is going to fall below, the diode will be off, right? So after that, diode cuts off. After that, diode cuts off. Right? Because diode will become reverse bias. Because diode will become reversed bias. And this will remain the same. This condition will remain the same until and unless my potential over here becomes greater than my potential over here, right? So potential in A needs to become more than B for the diode to become forward bias, right? So this situation will remain same until VA becomes greater than VB. So the point is, once it starts to drop, the diode becomes reverse bias. Okay, so interesting thing is, once it will start to drop and the diode becomes reverse bias, this means open circuit. Now we can see that what do we have now? We have a load resistor now connected in parallel to capacitor. So our circuit is still there. Now capacitor will start to discharge. Right, so capacitor will start to discharge through load resistor R. And now capacitor discharge, right? Because our diode will remain open circuit, so the capacitor discharge is going to remain this. So that phenomenon, that discharge is gonna happen until and unless this condition will become true and the charging will start again and the diode become forward bias again. Otherwise, the current is gonna continues to flow, and the capacitor discharging will continue to happen. Right, so capacitor discharge, so this will continue for almost the entire cycle until Vi exceeds capacitor voltage, right? Which essentially means this, right? Va over here is Vi, and Vb over here is essentially whatever the voltage that we have across a capacitor, Vc, right? Okay. So this phenomenon, this discharging film, is going to continue to be there unless the Vi will become more than the capacitor voltage, and then our diode will become again forward bias, and we're going to have start to have the charging phenomenon again. Okay, so interesting thing. So interesting thing is, if I will draw now the output is, so after reaching at this point, as it is going down, it is going to start to discharge, right? And this discharging will continue, right? And this is a peak value. Continue till this time. And so essentially it won't continue. Yeah. So let me draw this output essentially. On this waveform, it will be probably a little easier. Okay. So it will charge over here, then it will start to discharge, and it is going to continue to discharge until almost this point. And now what will happen at this point? At this point, this is my voltage across a capacitor, right? So V naught is, this is V naught. So this is the value of V naught, and now I can see that, or over here, this is the value over here at VB as well. VB, VC, you can call it anything. Okay, so we're here at this point now, our value of the V naught becomes less than value of the Vi. So if VB over here becomes less than the Va, it will become forward bias again. So during this cycle, so as soon as we are going to move beyond this point, the diode again becomes short circuit and the capacitor will charge again, right? So this charging is again going to start to happen. At this point, again moving below, it is going to start to the V naught again will become more than the Vi, and it will again stop charging, and then it will become open circuit, and our discharge cycle will continue. So essentially we're going to get again this thing, and then again this thing, and again this thing. So this is something that we get after connecting the load resistor and the capacitor. So we get kind of this ripple voltage. During the first cycle it will charge, and then we kind of get this continuously, this thing. Something like this, right? Okay. So let's talk more about this. All right. So one important thing to see over here is, so two things. We are going to calculate some of these values. So one value is something that we are going to define it over here. We're going to call this as VR, or a ripple voltage. So we will calculate the value of the ripple voltage shortly. And then interestingly, look at another important thing over here, which is called as the time constant. Right? So time constant of this RC circuit. Right? So we have this RC circuit over here. The time constant is CR. Okay, so if I will if I will make sure, in order to keep the output voltage from decreasing too much during capacitor discharge, we can select this. All right, if I will make sure, right, so our time period of the waveform is from here to here, right? So this is what we have as a time period of this waveform. If I will make sure that this condition, that's, sorry, going back here, that my CR would be very, very larger than that time period, then I will make sure that the discharging or the decrease in the voltage will be very smaller, right? So for example, if CR is very, very high, then my decrease is going to be smaller. If it is low, then the discharge will be here. Otherwise, the discharge will be here. The more it is closer to the time period, the higher it will, the quickly it will discharge, or it can discharge completely in that time period if it is equal. So what we want to make sure that it should be very higher than the time period, this constant, so the discharge will be very minimal. So we can also keep it even more minimal by keeping this value thing, by making this condition. So our CR needs to be extremely larger than the time period. All right. So this is one important consideration. Now let's look at some of the more equations. So another important thing is now the load current. Load current will be, so IL through the diode is V naught over R. So we can see it over the circuit. It will be, sorry, in this circuit, so it will be V naught over R. And we can see that the diode current is the sum of the capacitor current plus the load current, right? So diode current, when it will be on, will be a capacitor current plus the load current, and the capacitor current is C dV I by dt, sorry, plus the load current. So we can also write this equation as V naught over R. All right. So this is the amount of the diode current that is flowing through the diode. All right. So before I move forward with the ripple voltage calculation, I just wanna give you again a quick recap. Okay, over here. Sorry. Right, so the problem that we have after the full wave rectification is we still have a full wave rectification, a kind of a DC, but it was pulsating, so we cannot feed that to charge our circuits or our electronic equipment. So we needed to have a constant voltage. So we saw that capacitor plays a very important role in terms of minimizing these variations. So we, in this analysis over here in a peak rectifier circuit or a peak detector circuit, we saw that if we will just connect the capacitor after the diode, and over here we are assuming the diode to be ideal. So as soon as the voltage becomes greater than 0, or as soon as your positive cycle will start, capacitor will start to charge. And when this will reach to this peak voltage, capacitor will be fully charged. And as soon as this will fall down from the peak voltage, the diode becomes reverse biased open circuit, and our voltage will remain constant. And in this case, in this specific case, there is nothing after the capacitor for it to discharge, so our voltage will remain constant, indefinite. Again, that was kind of a very ideal situation, which is not true in real-time scenarios. So in a real-time scenario, we saw that our circuit is going to look like something like this, where we are going to have a voltage, where we are going to have a resistor or a load connected after the capacitor. All right, so when we look at that, we realize that now what will happen is, as our input voltage is increasing, our input voltage starts over here, the capacitor will start to charge. It will get fully charged when our input voltage reaches its maximum, right? When it reaches maximum, the capacitor is fully charged. As soon as it will start to fall below that, the diode becomes reverse biased open circuit, and our capacitor will start to discharge because there's a load connected to it. And that discharge interval, or the time, or the amount of the discharge, or the ripple voltage, the decrease from the peak voltage, it all depends on the time constant of this RC circuit. So we need to select the values of the resistance in the capacitor, or in this case, the time constant, such that it is significantly higher than the time period of this input waveform. If it is significantly higher than the input waveform, then we will make sure that our discharge is very minimal. And this is what is defining as variations, and because this is what we are going to feed it to the Zener. right? So we are going to have, so in this waveform we are going to have a mean value, and this is what our variations are. We want to make sure that these variations will be minimal, and we can make this minimal by making sure that we are going to have our RC, the product RC, the time constant here will be much larger than the time period of the waveform. Okay, so what will happen is after it will be discharged to a certain amount, and as soon as the input voltage will become again greater than the voltage that was reached after the discharging at point B, or the capacitor voltage, the charging will again start to happen. So that is why we see this kind of a ripple effect. We see increase, decrease, slight discharge, again charging, discharging, charging, discharging, and this process will continue. And this variation from the peak value is what is called as a ripple voltage. All right, so we are going to now find out what the kind of calculate what the ripple voltage is. Sorry. All right, so let's find out what is the value of the output voltage. Okay, so our output voltage now, if I will look over here, right, at this point my output voltage is approximately VP, it is fully charged, and at this point what is the value of the output voltage? It has been decreased. So let's define the kind of a ripple voltage. Sorry, just give me 1 second. Right, so I'm interested in finding the value of over here. At this point, let's call it as X, and at this point let's call it as Y. And then I wanna find out what is the average value of my output, right? So this is my output waveform, the V naught. So I want to find out what is the average value. So I'm going to find out what is the maximum, what is the voltage value at X point, and what is the voltage at Y point. So at X point, I know that the voltage value is V naught, and let's find out the value at the Y point. So the value at the Y point is, we have, so this is what we have, a ripple voltage here, right? So this, trying to keep it less messy, but this is the ripple voltage. So this is VP minus VR. So let me draw it over here again, right? So we have something like this, right? So this is VP, and or point, let's call this point X, this is point Y, and we are interested in finding the average of it, and this is our output waveform. At X point our peak value is VP, at Y point our value is, this is VR, the ripple voltage is VP minus VR, right? So the output voltage will be the average of these 2 points, so it will be VP plus VP minus VR and divided by 2. Okay, so 2 VP minus VR over 2. So the output voltage DC will be VP minus VR over 2. All right, so this is the output voltage that we have for the DC output voltage that we have for the waveform. Okay. All right, so now let's find expressions for, now we want to find out exactly what is the value of the VR ripple voltages. I'm just finding out the value of the VR and the diode currents, the maximum diode current and the average. All right, so now considering diode to be off, we are left with a parallel RC circuit, right? So we saw that in this circuit, when the diode becomes reverse bias, what we have is a simple, we have a capacitor here and we have a resistor here. So it's a parallel RC circuit. right? So the output voltage of the circuit, V naught, can be represented by an exponential decaying function with where our peak value is a Vp and E is equals to minus T over CR. Now we know that at end of the interval, at the end of the discharge interval, when T becomes equals to T, the output voltage becomes Vp minus VR. This is our point Y we are talking about, right? So our output voltage, I'm going to replace that over here. So my Vp minus VR becomes equals to Vp e raised to power T over CR. Essentially it's Vp minus VR is Vp raised to power capital T minus capital T over CR. This is the output voltage that we have. Now assuming CR to be very larger than T, this condition to be valid, we can use an approximation to open up, to simplify e raised to power minus T over CR. It will be approximately equals to 1 minus T over CR. Okay, so if we are going to put that over here, right, so Vp minus VR equals Vp minus Vp into T over CR. So Vp, so we are left with ripple voltage is equals to peak value T over CR. All right. Right, so this is how we can find out the value of the ripple voltage, and we know that since time is equals to 1 over frequency, you can also represent this ripple voltage as Vp over FCR. Okay, another formula, we also saw that that our load current equals to the peak value over R when V naught over R, right? When V naught becomes equals to Vp, so we can also replace it over here. Over here, Vp over R, we can replace that with load current, so it will become IL over FC, kind of another formula. I'm giving you all the formulas probably that you need. Okay, so I'm also so this is how we can determine the ripple voltage. If anything, you probably don't need to remember all the derivations of this ripple voltage. I will probably not ask in exams. However, please do note down these formulas, how you can calculate the ripple voltage, and so more importantly, what factors does the ripple voltage depend on, right? Of course, we already saw that the ripple voltage should depend on the CR factor, because this is what it is deciding. The amount of the discharge. We saw that the greater it is from the time period, the less discharge there will be. So ripple voltage, of course, depends on this time constant CR value. Of course, it also depends on the time period of the waveform, right? Because CR and T are kind of, that condition is kind of related on both of these parameters. And of course, our VR also depends on the value of the peak, the overall peak voltage value of the input waveform that we are trying to rectify. So Vp is the amount that the capacitor is discharged, charged to that level. Okay, so in that terms, it is very important, and you can, even if you don't know the formula, you can easily develop this relation by understanding the factors that it does depend on, and kind of a direct and indirect correlation that it has with it. I'm going to give you a couple of other expressions to remember. We are not going to derive it, but the derivations are in the book. I'm not going to ask the derivations in the exam as well, but if you're interested. So we are going to find that this is the average diode current that will flow, and that is equals to IL 1 plus pi square root of 2 Vp over Vr, and the maximum diode current will be IL 1 plus 2 pi 2 Vp divided by Vr. Alright, so also remember these current values. Again, I'm not going to ask the derivation exams, we didn't drive it in the lecture. Probably I can send a supplementary lecture on these derivations too. Alright, so there is one more thing before we kind of completely finish up our lecture today, and that is, so we saw that, so this is, so for example, we did this analysis was done for kind of a half wave rectification when we have just one diode connected, right? One diode is going to provide us a half wave rectifier circuit. So what if we are going to have a full wave rectifier with a filter attached, right? So what if we have a full wave peak rectifier? So we are not going to do all the details, but everything will remain the same, except that now we will realize that once we have a full wave rectifier, and this will be my input waveform, the time period of this waveform, right, has been reduced by half after full wave rectification, right? So my initial ripple voltage was equals to Vp over FCR over here, Vp over FCR. So now all I need to do is to make sure that, so the time period has been reduced by 2, or frequency has been increased by 2. So my new rectifier voltage for this case will be Vp over 2 FCR. Right, so it's this simple. If you have to find the ripple voltage for a full wave peak rectifier, the time period essentially reduced to half, or the frequency doubles. And similarly, I can also give you the expressions for the diode average current and the diode maximum currents. It will also be, the similar effect is going to happen with it in terms of frequency and time period. So 1 plus pi, now it is Vp over 2 Vr, and the maximum value of the current is IL 1 plus 2 pi Vp over 2 Vr. Alright, so these are the diode currents. And the ripple voltage, essentially, all we did in the ripple voltage is that we use exactly the same formula and we just divide it by half, because the time period has been reduced by half, or the frequency has doubled. Okay, in terms of the waveform, let's quickly look at the waveform. Right, for example, if this is my now input waveform, okay, yeah, I should do a slightly better job at drawing. Okay, so this is the full wave rectification, and now assuming that in the very first cycle your charging will happen, so after that, or we can make this as the first cycle, right? So it is going to charge, then it is going to discharge over here, it is going to charge again, it is going to discharge over here, charge again, discharge, right? And again, this is your ripple voltage. Now you can see that the time period, or the frequency of this, the time period has been reduced to half in this waveform, and the frequency has doubled for both the input and the outputs. So that's the only thing to remember for the full wave peak rectifier. And also essentially what we ended up doing is we ended up generating this waveform, and we have seen that if I am going to feed this waveform with some average value and variations to my Zener shunt regulator, it is going to generate a very constant waveform with a very minimal variation. There's going to be another, let's say 0.5% variation there, but that will be good enough to charge our equipments. Okay, all right, so with that we are going to finish up this lecture, and I will talk to you in the next lecture. We have just a couple of applications left, and next lecture will be a short one. All right, thank you so much. Bye bye.